So vector calculus lecture 23, and the remaining topics that we're covering are in chapter 17. Sections 1 to 4. And we talk about vector valued functions or vector fields, line integrals, a particular important class of vector fields, which are called conservative fields. So conservative vector fields and potential functions. And what puts it all together, connects them all, and gives a kind of generalization of the fundamental theorem of calculus to functions of several variables, at least in 2 dimensions, is Green's theorem. So all of these are important. Give them a star, and that's what we are discussing. So let me review what I did last class on vector fields and look at some of the problems. So a vector field simply assigns a vector to every point in R2 or R3. And we're going to mostly look at R2, which is the XY plane. And we have a function f of xy. So you take a vector in the plane, xy, and the vector field assigns a vector to the vector xy. So if you take a point xy, f of xy will be another vector in the field. Let's say we write its first coordinate as little f of xy and its second coordinate of little g of xy. Or you can write that as f of xy I plus g of xy j, right? This is in R2 in the plane. So, and that's all a vector field is. One very special kind of vector field is a radial vector field. Which sends every vector to a vector parallel to itself. And a particular kind of vector field would be f of xy if we let the vector r be xy. This is r divided by some power of its length. So this means at every point, you assign a vector in the same direction as the vector you're starting from. This is a radial vector field. It's just, if you take a vector r, you assign it to some vector parallel to itself. It could be in the opposite direction, but it's certainly on the line through the origin through r. That's all a vector field is. And here's a very nice example of a vector field. It's called a rotation. It's called the rotation field. So the rotation vector field that f of xy be equal to minus y x. So let me draw some of the vectors in this vector field. It might be easier to draw if I use some graph paper. So let me do that. Okay. So here we have R2. So this is the point 1, 1. So if we have the vector field f of xy equal minus yx, f at, actually, let me start here. F of 1, 0, x is 1 and y is 0, so this is 0, 1. So at this point, the vector is pointing up. F of 2, 0 is 0, 2. So at this point, the vector is pointing up. F of 3, 0 is 0, 3. So at this point, the vector is pointing up, the headland 3, and so forth. F of 0, 0 is just 0, 0. F of minus 1, 0 is 0, minus 1. F of minus 2, 0 is 0, minus 2. So at each point in the plane, I'm starting to draw vectors, the vector assigned to that point. Let's see, what about on the y-axis? F of 0, 1 is minus 1, 0. F of 0, 2 is minus 2, 0. F of 0, minus 1 is 1, 0. F of 0, minus 2 is 2, 0. Let's see, what about on the line y equals x? F of 1, 1 is minus 1, 1. Let me draw that in red to make it less. So at the point 1, 1, that's right here, the vector is minus 1, 1. It's going up right there. F at 2, 2 is minus 2, 2. So it's going over 2 and up 2. F of what about f of minus 1, 1? When y is 1, this is -1. And when x is 1, -1, this is -1. So at the point -1, 1 here, the vector is -1, -1. So this. What about at f of -1, -1? That's 1, -1. What about f of 1 minus 1? When y is -1, minus y is +1, and x is 1. So f of 1 minus 1 is going to be okay. And you can see a lot more pictures in the more detail in the text. In the text, you can look at my text is figure 17.6 on page 1091. So this is the rotation field. It assigns a vector to every point. And that's all it is. Right? So a vector field assigns a vector to every vector. Any questions about that? Now, what's very interesting is, oh, let me just say one other thing. Suppose we have phi of xy to be some scalar valued function. Like phi of xy equals x squared plus y squared. We defined the gradient of phi. This is the function, this is vector value. The gradient of phi at xy, you take the partial derivative of, this is in general, partial phi with respect to x, partial derivative of phi with respect to y. You differentiate this with respect to x, you get 2x. You differentiate this with respect to y, you get 2y, which is a vector in R2. So the gradient of a scalar field is a vector field. And sometimes a vector field is the gradient of some scalar field. So for example, suppose we have the vector field f of xy equals three x squared plus y x. This is a vector field. The vector xy gets sent to 3x squared plus y, x. And I claim this is the gradient of a function. So if we were to let phi of xy be the scalar field x cubed plus x times y, the partial derivative of phi with respect to x, like partial phi partial x, is 3x squared plus y. And the partial derivative of phi with respect to y is x. That's exactly what we have here. So this is the gradient of the scalar field phi. So here we started with the vector field, and it turns out there is a scalar function phi such that the gradient of phi is f. And this is just an important definition. We'll come back to it again a bit later, but the vector field F is called conservative. And this is conservative not as in politics, but as in, for example, physics, where you learn about the conservation of energy. The vector field F is conservative if there exists a scalar field, a real valued function, a scalar field phi, such that the gradient of phi gives you the vector field. And in this case, phi is called a potential function. Again, if you study some physics, you learn about electrical potential, gravitational potential, potential energy. Phi is called a potential function for F. So whenever you have a scalar function phi, its gradient is a vector field. And if the vector field is the gradient of some scalar field, we say the vector field is conservative and the scalar field is a potential function for the vector field. And a standard problem in vector calculus is, given a vector field F, determine if it is conservative, and if it is conservative, compute a potential function. And we'll see in connection with line integrals that this is really very important. So this brings us to line integrals. And what we mean by a line is a curve in R2. So you have some curve C, which is some function given by some function R of t, with coordinates x of t, y of t, where t runs from A to B. So this is R of A, and you end up at R of B. And a typical point on the curve is R of t. So this is a curve. And the length of the curve C is given by, well, let's say the length of the curve C from t equal A to some number t. So you started with t equal A. If you want to think of this as a particle moving at time t, at time A, here's where the particle is. And as t increases, the particle is moving along some curve in the plane. At t equal b, at the end, you end up over here. But at any given time t, you've moved some distance along the curve, and the distance you've traveled from time A to time t, we'll call s of t. And this is given by the integral from A to t of r prime of u, absolute value, du, which is just another way of giving the length formula that we've seen before. The length of r prime of u, if this is r of t, r prime of t is just r of t is x of t, y of t. Then the tangent at any time t, the derivative, is x prime of t, y prime of t. And the length of this vector is always the square root of the sum of the squares of the coordinates, x prime of t squared plus y prime of t squared. So that's what this is. This is square root of x prime of u squared plus y prime of u squared du. So this is the length of the curve from time A to time t. And just by the fundamental theorem of calculus, if we differentiate this, ds dt is the square root of x prime of t squared plus y prime of t squared. Or in the sloppy way we do like sometimes, ds is square root of x prime of t squared plus y prime of t squared dt. So this is just a little summary of how you find the length of any curve. And what we mean by a scale or line integral. So we have a scalar valued function. F. So f of x, y is a number. And so we have a scalar valued function f, and we have a smooth curve that just means you can differentiate its coordinate function c, given by r of t equals x of t, y of t. So we have this curve c in the plane, r of a ending in r of b. And the line integral, we wanted to find the line integral over the curve c of the function f of x of t, y of t, ds. It's the integral of the function over the curve. And if you remember, or if you recall, as I described very a bit last week, the way you count what this line integral means is you take each piece of the curve, take the curve, break it up into a little piece. Each little piece has some length, delta s. Take the value of the function at some point on the curve, f at some point there. And so if you have on this curve, this is f of r of tk. Is this point on the curve, and you evaluate f at that. So if you were to break this curve up into a lot of little pieces, and in each piece take the length of the curve times the value of the function at some point on that curve, and you add that up over all the pieces, and you take more and more pieces, just as you do for the ordinary integral in Math 175 and Math 176. This is what would be called the line integral. But there's a simple formula to calculate that, which is this is equal to the, or you could even, if you like, take this as a definition, the integral from a to b of f of x of t, y of t, ds, which is the length of r prime of t, dt. So the simplest thing is a somewhat complicated formula, but the formula you have to memorize. You have to know the formula. This is how you calculate a line integral of a scalar function along the curve. And the simplest thing to do is to do some examples. So let's see what is a nice example perhaps to pick. Let me actually do a couple of the homework problems. So this is in section 17.2. Number 17. Number 17 is to compute along a curve C, x, y, ds, where C is given by the function r of t equals cosine t sine t for t from 0 to 2 pi. So by now you should know that this describes exactly the unit circle. When t is 0, you're at the point 1, 0. When t is pi over 2, you're at the point 0, 1. When you get to pi, you're at the point minus 1, 0. When you get to 3 pi over 2, you're at the point 0, minus 1. So as t goes from 0 to 2 pi, you're starting at the point 1, 0, and you're moving around the circle. And my scalar function that I'm integrating is f of x comma y. It's just x times y. So f of x of t, y of t. So for my curve C, the x coordinate is cosine t, the y coordinate is sine t. So x times y is cosine t sine t. So the integral around C of the function xy ds, if we apply this formula, this is the integral from 0 to 2 pi, f of x of t, y of t, that's cosine t sine t, times the length of r prime of t. Well, if r of t is cosine t sine t, when you differentiate this vector value function, this curve, the derivative of the cosine is minus sine t, derivative of sine t is cosine t, and the absolute value of this is 1. It's just another point on the inner circle. So it's cosine t sine t times 1 dt. So we have to do this integral. Now, 2 cosine t sine t, we know. So if I write 2 times a half, I haven't changed anything. So this is 1/2 the integral from 0 to 2 pi. 2 cosine t sine t is the sine of 2t dt. What's the antiderivative of the sine? It's minus the cosine. What's the antiderivative of the sine of 2c? It's minus 1/2 cosine of 2t. You differentiate this, you get sine 2t. And we're evaluating this from 0 to 2 pi. So this is minus 1/4 cosine of 4 pi, 2 times 2 pi, minus cosine of 0, which is minus 1/4, 1 minus 1, which is 0. So the value of this line integral is 0. So let me just pause for a second, and you should take a look at how I calculate this. And because this is exactly one of the types of problems you'll have on the final exam. You do need to know how to compute a line integral. So look at that for a second and ask me a question if you have a question. Okay. Any questions? If not, then we'll do another one, another line integral. Now let's look at number 19. So I want to find the integral of the function 2x plus y along a certain curve C, and C is the line segment given by r of t equals 3t, 4t, as t goes from 0 to 2. Let's say 0, 2, 4, 6, 2, 4, 6, 8. When t is 0, r of 0 is 3 times 0, 4 times 0, which is 0, 0. So we're starting at the origin. And where do we end up? Let's see. R of 1 is 3 times 1, 4 times 1, which is 3, 4. And where you end up, R of 2 is 3 times 2, 4 times 2 is 6, 8. So this curve is really a straight line starting at 0, 0, and you're moving along a straight line from here to here. That's my curve C. If this is R of t, R prime of t, you differentiate with respect to t, derivative of 3t is 3, derivative of 4t is 4. The length of this vector for LT is square root of 3 squared plus 4 squared, which is the square root of 25, which is fun. So we have our formula, the integral of 2x plus y ds along this curve is the integral as t goes from 0 to 2. 2x for this function, x of t is 3t, y of t is 4t. So 2x plus y is 2 times 3t plus y, which is 4t, times r prime of t, absolute value, 5, dt. Let's see, this is 6 plus 4 is 10 times 5. That's 50 times the integral from 0 to 2 of t dt. The integral of t is a half t squared from 0 to 2. Let's see, t squared is 4. 4 over 2 is 2, and 2 times 50 is 100. So the value of this line integral is 100. Let's look at another one, not one of the homeworks. Number 23. We have the integral along a curve C of y minus z ds. And the curve C is the helix. Actually, I don't log this. R of t is given by 3 cosine t, 3 sine t, 4t. As t goes from 0 to 2 pi. So this is actually a curve in 3-dimensional space. When t is 0, you're at the point 3, 0, 0. And as t increases, you're going around a circle but moving up at the same time. So you're going around what is called a helix. And from t going from 0 to 2 pi, that's 1 revolution. So you're starting here. This is r of 0. And at 2 pi, you're at the point, when t is 2 pi, this is 3 times 1, 3 times 0, 8 pi. This is 3, 0. You're moving around 1 loop of this helix. So for this function, x of t is cosine t, y of t is 3 sine t, and z of t is 4t. And the derivative r prime of t of this function, derivative of 3 cosine t is minus 3 sine t. Derivative of 3 sine t is 3 cosine t. Derivative of 4t is 4. And the length of this vector is the square root of this square plus this square plus this square. 9 sine squared t plus 9 cosine squared t plus 16. Sine squared plus cosine squared is 1. This is the square root of 9 plus 16, which is 5. So this integral is the integral of f of x of t, y of t, z of t, absolute value r prime of t dt from 0 to 2 pi. This is equal to what? Y minus z. Y is 3 sine t. Z is 4t times the length of r prime of t, which is 5, dt from 0 to 2 pi. Let's see, what is this? 5 times 3 is 15. The integral of the sine is minus the cosine from 0 to 2 pi. Minus 20, 4 times 5. The integral of t is t squared over 2 from 0 to 2 pi. So what is that? This is 1 minus 1, this is 0. So this is minus 20 over 2 t squared, 4 pi squared. So that's minus 40 pi squared, I think. That's what we got. Okay. So this is what we've been looking at as the line integral of a scalar field f along a curve C given by some function r of t. So let me just again write down the formula. The integral of C f of x, y ds is, so r of t, t going from a to b. This is the integral from a to b of f of x of t, y of t, absolute value of the length of the tangent vector, dt. So this is the formula for the line integral of a scalar field. Well, we also have vector fields. And we want to be able to also define and compute the line integral of a vector field. F of xy, so it's equal to f of xy, d of xy, along the curve C, given by the function r of t equals x of t, y of t, for t between a and b. We're going to use this notation, the integral along the curve C of f dot dr. So this is defined so what is this going to mean? We can do this in 2 dimensions or 3 dimensions. And so here we have our curve C. And at each point on the curve, this is the point R of T. And we have the tangent vector at R of T, which is R prime of T, the derivative. And if this is different from 0, if we divide by its length, this is the unit tangent vector at the point T, because this vector has length 1. And we use capital T to denote the unit tangent vector. That's the unit tangent vector. Let's take a simple example. Suppose R of T, we just take the first quarter of the circle, the unit circle. So R of T is given by cosine T sine T. Its derivative is minus sine T, differentiate, minus sine T, cosine T. The length of this is 1 square root of sine squared T plus cosine squared T, which is 1. So the unit tangent vector on this semicircle or quarter circle is the tangent vector divided by 1 is simply minus sine T cosine T. So the unit tangent vector at 0 is 0, 1. The unit tangent vector, for example, at pi over 4, it's this point on the semicircle, is sine pi over 4, cosine pi over 4 are both 1 over root 2 minus 1 over root 2 plus 1 over root 2. That's the unit vector in this direction. The tangent vector at this point, of course, you can see it's going to have to be horizontal going in that direction. The unit tangent vector at pi over 2, and T is pi over 2, this is 0, sorry, pi over 2, this is minus 1, 0. That's exactly what that is. So this is the definition of the unit tangent vector to a curve at a point. And for a vector field, the line integral of a vector field I'm going to go over C. So we know how to find the line integral of a scalar field. And if we take the dot product of the vector field with the unit tangent vector at any point, that's a scalar field ds. So this is the definition of the line integral of a vector field of a smooth curve. Let's see. No. This is the same as the integral around C of f dot product. The tangent vector is r prime of t over the length of r prime of t. Boy, let me write it more carefully. If r of t is given by x of t, y of t, for t between a and b, this is the integral from a to b of f dot r prime of t over the length of r prime of t ds, but we saw that ds is the length of r prime of t dt. And then these cancel. So we get what is really a simple formula for the line integral of the vector field is the integral from a to b of f dot r prime of t dt. Integral from a to b. So let's say this is a vector field f of xy is f of xy, g of xy. Those are the coordinate functions. So what we have here is f of x of t, y of t, dot product with r prime of t dt. This is the integral from a to b. Again, we can write this as little f of x of t, x of t, f of x of t, y of t, but comma, let me write this on a bigger piece of paper. So we have a vector field f of xy with coordinate functions lowercase f and lowercase g. So for every vector xy, we get a vector capital F of xy. And we have a function r of t, the curve x of t, y of t, the t between a and b. And the integral along the curve c of f dot t ds. This is the dot product of the vector field with the unit tangent vector. So that's a scalar. So this is reduced to the line integral of a scalar function. Let me just do this. What is f dot t? So this is f of x of t, y of t, comma g of x of t, y of t, dot product with r prime of t divided by the length of this vector. So when I compute this dot product, I get f of x of t, y of t times x prime of t plus g of x of t, y of t, y prime of t divided by r prime of t magnitude. Again, really, there's a lot to write down, and I'm filling in a lot of the details, which being left out of the text, I think. This is simply, this is, you can write this as f of t dot x prime of t plus g of t y prime of t. So this is what we're integrating. So the integral around the curve of this vector field, f dot t ds, is the integral of this scalar function. So this is the integral from a to b of f of t x prime of t plus g of t y prime of t 1 over the length of r prime of t times the length of r prime of t dt. These cancel. So we're left with something which is much simpler to look at. This is the integral from a to b of f of t x prime of t dt plus y of t y prime of t dt. If you think of x prime of t dt, x prime is dx dt over dt. You can somehow abbreviate this as if these cancels, this is dx. So what you often find as a shorthand for the line integral, this is purely notation. This is the integral of c f dx plus g dy. Now, there's an overwhelming amount of notation, but let me do some examples, and that I hope will teach you how to solve these problems and make things easier. Doesn't make it easy, but it makes it, I think, easier. So suppose we have the vector field f of x, y equal y minus x comma x. And suppose we take as our curve C1 to be the quarter circle that we looked at a moment ago. Start with the point P with coordinates 1, 0. And we move around the circle to the point Q with coordinates 0, 1. And we can parametrize this by r of t equals cosine t sine t for t from 0 to pi over 2. R prime of t is minus sine t, just differentiate each of these coordinates, cosine t. And the length of r prime of t is 1. And I want to compute the line integral. So this is the curve C1. I want to compute the line integral along the curve of f dot t ds. So for the function f of x minus f of x y equal y minus x x, the first coordinate f of x y is y minus x. The second coordinate g of x y is just x. And f, which is y minus x comma x, y is sine t, x is cosine t. So this is the function of t. This is sine t minus cosine t, and x is cosine t. So f dot r prime of t, this is the same as f dot t. If the unit tangent vector is just r prime of t. This is the inner product, the dot product, sine t minus cosine t comma cosine t. Dot product with r prime, which is minus sine t cosine t. So the dot product, and multiply the first coordinates, sine t minus cosine t into minus sine t, plus cosine t times cosine t. So I get cosine squared t minus sine squared t plus sine t cosine t. And cosine squared minus sine squared is the cosine of 2t, and sine 2t is, minus sine minus cosine times minus sine is minus sine squared plus sine times cosine. No, this is right. This is cosine 2t plus a half sine of 2t. So my integral, f dot t ds, along this curve C1, is the integral from 0 to pi over 2 cosine 2t plus a half sine 2t dt. The integral of cosine 2t is a half sine 2t. The integral of a half cosine 2t is minus a fourth cosine 2t. Evaluated from 0 to pi over 2. Let's see, sine pi and sine 0, this gives 0. So I get minus a fourth cosine of pi minus cosine 0. Minus 1 is minus 2 times minus a fourth is plus a half. So as I computed the integral, this is what it gets. Let me do another example. Pick one from the homework. So this is in the homework number 41. So we have the function, the vector field f equal to xy. And the curve C is going to be the parabola r of t equal to 4t t squared, as t goes from 0 to 1. So in this parabola, the first coordinate, x of t, is 4t. The second coordinate, y of t, is t squared. You want to convince yourself that it's a parabola. If y is t squared and t is x over 4, this is x squared over 16. So what does this parabola look like? Is that this is the parabola. It looks like this: y equals x squared over 16. When x is 1, this is the point 1 over 16. Sorry, that's what x is. But this is the parabola. So as t goes from 0 to 1, r of 0 is 4 times 0, 0 squared, which is 0, 0. R at time 1 is 4 times 1, 1 squared, which is 4, 1. So 1, 2, 3, 4. This is 1. So we're going along the parabola from the point 0, 0 to the point 4, 1. That's R. R prime of t, when I differentiate, derivative of 4t is 4, and the derivative of t squared is 2t. So the length r prime of t is the square root of 4 squared plus 2t squared, which is the square root of 16 plus 4t squared. So the unit tangent vector is 4 2t divided by square root of 16 plus 4t squared. But the integral along the curve C1 of f dot t ds, along this curve C, is what? It's going to be f of xy is equal to xy. So x of t is x, y of t is y. X is equal to 4t. Y is equal to t squared. So my function f is a function of t is 4t t squared. So let's use one of our formulas. This is the integral from a to b. A is 0, b is 1. The integral from 0 to 1. F of t, x prime of t, plus g of t, y prime of t, dt. The first coordinate of my function f of t is x of t is 4t. X prime of t, x is 4t, x prime is 4. G of t is y is t squared, y prime of t is 2t dt. So this is the integral from 0 to 1 of 16t plus 2t cubed dt. So I reduce everything to simple integration. The integral of 16t is 8t squared. The integral of 2t cubed is a half t to the fourth. Evaluated from 0 to 1, I get 8 plus a half, which is 17 over half. 17 over 2. Okay, let me just go through this problem again as carefully as I can, because this is really complicated technique to master. So, this is 17.2, number 41. We have a vector field F, where f of xy is just xy. So this sends every vector to itself. And we have a curve parametrized by a function r of t, which is 4t t squared, for t going from 0 to 1. So x of t is 4t. Y of t is t squared. R prime of t is 4 2t. That is, dx dt is 4, dy dt is 2t. So this is r prime of t. So the integral along the curve of f dot t ds is the integral from a to b of the dot product of the vector field f with the tangent vector r prime of t dt. F is xy. As a function of t, this is 4t comma t squared. So here I have the integral a and b, there's 0 and 1. F 4t comma t squared dot product with r prime of t, which is 4 comma 2t dt. So this is my vector field as a function of t. And this is r prime of t. If I take this dot product, 4t times 4 is 16t, t squared times 2t is 2t cubed, dt. This is just a simple integral to compute. This is 8t squared plus 2/4 or a half t to the fourth, evaluated from 0 to 1, which is 8 plus a half, or 17 over 2. That's the line. Now, if you study some physics, work is force times distance. So if you have F as a force acting on a particle, and you have a curve C given by some function R of t, So you have some force field, and you have a particle moving along some trajectory c. And at any given point, the work done by the force on the particle, so let's say this is the vector f at that point, but you want to find a component of f in the direction of motion. So the projection of f here is exactly it's the component of force in the direction of motion. So the work being done on the particle as it moves along the curve from here to here is exactly the integral around the curve. So one physical interpretation of this line integral is you have a particle moving in a force field, there's some force, and the work being done by the force on the particle as it moves along c is exactly this integral. So there's nothing special about this, but this is just one of the important definitions of one of the ways you calculate work in physics. It's always a line integral. So if a particle is moving through some force field, the work being done as it moves along the curve is exactly given by this line integral. Now, I should mention there's a second type of line integral of a vector field, which is flux. So actually, maybe just to introduce the words. Suppose we have a closed curve. Closed curve is a curve that ends up where it starts. So here you have R with A, and as you move along this curve, at time B, you're back where you started. That's what a closed curve is. And you have a vector field F, what is called the circulation of F on C is the integral around this closed curve, F dot T ds. So the line integral along a closed curve has another name. It's just a name. It's called circulation. But there's also something called flux. And we only define this for a curve that doesn't intersect itself. So here we have a curve C. Which is non-intersecting. It does not intersect itself. And the flux of the vector field across C is defined as follows. So recall that the integral of F dot T ds along this curve is, you can write this as the integral from A to B of f dx plus g dy. And the second integral is f dot n. I'll explain n. I guess I don't have time today, but it's on Wednesday. This is the integral of f dy minus g dx. And in this case, what we want to do is if you have your curve, You always have the tangent vector, which is, this is the unit tangent vector on the curve. But I want a unit vector perpendicular to the tangent vector. And that normal vector is n. So we're integrating at every point on the curve, you want to find a unit vector perpendicular or normal to the tangent vector. And the integral of f dot n ds is what is called the flux. But at least for today, this is the definition of the flux. And I'll work out some problems on that on Wednesday. Let me just state one last result, because in some sense, the sooner you see it, the better. We call a vector field F is conservative if F is the gradient of phi of a scalar function phi. So if a vector field comes by taking the gradient of a scalar field, then it's called conservative, and phi is called a potential function. With the vector field F. And what is the fundamental theorem of calculus in 2 dimensions? So this is the fundamental theorem for line integrals. It says the following. If you have a curve C from A to B, this is the point A, this is the point B. If F is the gradient of phi, then the integral along the curve C of f dot t ds only depends on the endpoints of the function. If this is phi of B minus phi of A. So here we have a curve from A to B, but if f is a conservative vector field with the potential function phi, the integral from A to B is just the value of phi at the endpoints. And what this says is very important. If you have another curve, C2, or this C1, from A to B, again, the integral around C2, f dot t ds, is the same thing, the difference at the endpoints, which means the value of the line integral from A to B is independent of the curve. With any curve you take from A to B, the function takes the same value, which also has the following corollary. You have a closed curve C from A to itself. The integral of f dot t ds along this closed curve C is always going to be 0. If f is a conservative vector field. Because if you took a point B on the curve, the integral from here to here would be one thing, the integral from here to here would be the same thing. In the opposite direction, it would be the negative, and then you would get 0. So for a conservative vector field, the integral around any closed curve is 0. And the integral from one point A to another point P is independent of the path. And this is the fundamental theorem for line integrals. And it's really a very, very interesting result. And again, if you study physics or engineering, a lot of applied fields, you use this all the time. Anyway, as I said and keep saying, in sections 7.17.1 to 4, there was a lot to think about. And I encourage you to take advantage of the Zoom problem sessions that I have this week, Monday, Tuesday, Wednesday at 7 p.m. And if you have a question, you can't make it at one of those times, I encourage you to send me an email and we can arrange a time where I can meet with you privately. Any questions before we quit for the day? Okay, see you Wednesday. Bye now.